So today's webinar is on the topic Accelerate Simulations with Altair SimLab Automation. So in the today's webinar, we'll be covering these topics. First, we will go through the various solvers that Altair has under the CFD portfolio. Then we will discuss about the SimLab and its CFD capabilities. Then we'll discuss more about the automation part in the SimLab user interface. Then I have few live demonstrations to do for you, and then I have a case study to show. Then we can have a question and answers discussion in the end. Yeah, so with this, let's get started with the today's webinar. Okay, so before jumping to the webinar topic, let me give a short introduction about Meson Labs. So we are the official channel partner for the Altair technology. Altair has more than 150 plus products in their portfolio. So we are the bridge between the Altair and the customers. We have great team with great experience. We have people with 25 plus years of experience in the industry. We started functioning from the last year and we have 30 plus customers and we are growing every day. Yeah. So let me take you through the Altair CFD solvers. So Altair CFD offers a complete set of tools to support everything from detailed component analysis to complete system performance. So we have various solvers for the various applications. So in the first, let me take my laser. So here we have Altair AccuSolve, which is the multidisciplinary CFD solver. Then we have UltraFluidX, we have NanoFluidX, Flow Simulator, and ElectroFlow. So AccuSolve is for the multidisciplinary CFD solver. It has a wide range of capabilities to handle a variety of industrial applications. It also offers additional multiphysics capabilities by interacting with other Altair solvers. Then we have UltraFluidX, which is specifically designed for the external aerodynamic case. So from the design part of view for the ground vehicles, aerodynamic coefficients, they play a critical part in the design. So we have a special solver that is UltraFluidX, which is built for the same. So it is based on the LBM method and it is GPU optimized solver. So it is extremely fast and efficient. Next in the portfolio, we have NanoFluidX, which is based on the SPH method. So some of the key applications where NanoFluidX can be used are water wading simulations. You can imagine by looking at the image in this slide. This is the water wading simulations. These kind of simulations you can perform using the NanoFluidX. Then you can also do drivetrain oil management simulations and many more with the NanoFluidX. Then in the list for the electrical components for the circuits, we have Flow Simulator and ElectroFlow under the CFD portfolio. So in the today's webinar, we will be focusing more on the AccuSolve, which is general purpose multidisciplinary CFD solver. So we will perform CFD simulations using AccuSolve. Yeah, just like I mentioned in the previous slide, AccuSolve can handle wide range of applications. You can use this solver for number of CFD simulations, which include heat exchangers. You can do headlamp thermal simulations, engine cooling simulations, battery thermal, and multi-phase simulations, and many more. So it is not limited to any specific type of applications. It can handle a number of applications. Yeah, so we spoke about the solvers, different solvers that Altair has, but whenever we have a model, we cannot directly submit job to the solver. We need a preprocessor. So we have two preprocessors for the CFD purpose. So one is HyperMesh CFD, and then we have the SimLab. So both the preprocessors are unique. So SimLab CFD offers multiphysics. You can couple the AccuSolve with other available solvers and perform the complete set of simulations. Whereas Hypermesh CFD, in Hypermesh CFD, it is more on the AccuSolve part. It is for the flow and thermal simulations alone you can perform in the HMCFD. So in that way, these two user interfaces are developed. So please don't get confused between HMCFD, SimLab, AccuSolve. We have solvers and we have preprocessors. First, we do entire modeling in the preprocessor, and then we go and submit the job to the solver. So yeah, this is the Altair SimLab. So we have you can see the solutions in the ribbon. We have structures, thermal, flow, and we have electromagnetics. These are different solvers, and you can couple one solver to the another. That is the advantage of using Altair SimLab. So in the today's webinar, I will be using SimLab user interface. I will be performing the simulations in the SimLab user interface, and I will be showing you the automation capabilities of SimLab. Okay, now let's move into the core topic of the today's webinar. So before directly coming to this topic, I just wanted to say more on the solver part and the preprocessor part. That is why I included few slides uh, just to ensure that everything is understandable. Okay, so these are some of the prerequisites which you can say for the today's webinar. So if you are familiar with the SimLab user interface, if you know SimLab user interface very well, then you will understand the things better. So yeah, you can also see not prerequisites. Please don't get panic by hearing the words like Python, scripting, automation. I can completely understand that we all come from the mechanical engineering background. So prior knowledge in Python or any other language is not necessary for this webinar. You will completely understand whatever I am doing. Yeah. So for any CFD, for any, what to say? Mm, if you want to perform any CFD simulation in SimLab, you have to follow these 4 steps. Once you have your model with you, you cannot directly go to the solver. You need to do the meshing, you need to maintain the quality, and then you go and then you need to set up the simulation. You need to provide the materials, boundary conditions, and then you submit the job to the solver. Then in the end, you get the results. So at this point of time, you can imagine the different stages of CFD simulation and the number of time that it takes for one simulation to do. So you may commit mistake in any one stages, and in the end, when you run the simulation and you get the result, then entire simulation result is wrong because you committed mistake somewhere in the setup, or it may be in the meshing, or meshing quality might not be good. So anything can happen. So what if I tell you, I provide you a script and you have a model, you just run that script. All these steps are performed using a script in a single click. You don't have to interfere at all. So that is what we are going to see in the today's session. So that is what is the automation part of the CFD simulation. Yeah, I will be explaining you more in a live user interface. You will understand it better. So, but keep in mind, these steps you need to follow for any CFD simulation that you are doing. Okay. So let me boost your curiosity by performing this activity. I call it a magic script because it does entire job for me. Whatever the steps I mentioned in the previous slide, it does completely without my intervention. So in this slide, you can see there is one problem that is it is a manifold pipe. It is analogous to the inlet manifold of an engine. What it does is whatever the flow is incoming from this section, it equally distributes among the four outlets. So there is one inlet here. We can see water is the material here, water inflow at 2 meters per second. Then we have four outlets, 1, 2, 3, 4. So what is my aim is, I have a script and I have a model. So I want that script to perform all the steps that are mentioned in this slide and give me the results directly. Yes, that is possible. That is what we are going to see. So let me go through the SimLab and perform that for you. So I'm using 2024 version here. Give me a moment. Yeah, just like Kavana mentioned, in case if you have any doubts, please post them in the chat section. I will have a look at them in the end and answer. Yeah. So this is my SimLab user interface. This is how it looks once you start. So here is the model browser. Here there is selection list, output list, here Python window. Yeah, so let me run a script and show it for you. So I'm going to a folder. I'm going to a folder called manifold. What I have here is I have an input folder, output folder, and I have a report. So in the input, you can see there are two things. One is CAD, that is manifold fluid. So it is the model. It is in the parasolid format. Then I have my script. I will let me not open the script now because I'm going to discuss it in detail in the next upcoming slides. Let me just run the script and just show you how it actually works. So I will do one thing. I will copy these two. Copy. I will paste them in the output. So right now you can see my output folder is completely empty. So what I'm doing is I'm simply pasting it here. So I will run the script. So how to run that? So let me go through SimLab. Here you can see there is an automation ribbon here. Yeah. Automation, scripting, and here you say there is play, then auto. Then what I'm going to do is I'm going to select that Python script. Manifold output. Yeah, I'm going to just click on this and say open. Yeah, now you can see how it is doing all the activities automatically. It is imported. You can see the status in the left bottom here. It is currently doing the meshing. Mesh is complete. You can see in the modeling browser. Now, next, it is going to create a solution that is, sorry, it will create a volume mesh now. Currently, surface mesh is complete. You can see the icon here. Yeah, now the surface mesh icon is changed. The ribbons are changed. Volume mesh is complete. The analysis ribbon is changed. CFD solution is set up. It is still running. Now it is running the simulation. Yeah, it takes few minutes, just like 1 or 2 minutes. It is very fast. I'm doing nothing. I just clicked on the script. It is doing entire job on its own. Yeah, now you can see the simulation is complete and it is extracting few results which I have mentioned in the script. Yeah, now you can see the simulation is totally complete now. In this solution, you can see result is complete. Let me go to my output folder and see what actually happened. This was my output folder. I had only model and the Python script, but you can see there are various files which are automatically written. I have commands to save my files in between. So it has saved after importing, after setting up, and after the solution is completely run. So you can see the log file here. It is actually a best practice to go through the log file to see what steps are completed. So you can see unit is set, parasolid is imported, export is done, transform is done, surface is done. Passed means all the stages are complete successfully. So this is my automation log. Now let me take you through the report, what report it has created. Even I didn't create a report on my own. Script has done everything for me. It has given a title, manifold flow CFD report. Here I have velocity counter. Next I have pressure counter. Next I have slice plane. Whatever section I have mentioned in the script, it has directly given me the results. Isn't it amazing? Uh, that is what we will go through in the upcoming section, how to generate this script and how to automate this entire kind of simulation. So let me close this. Yeah, so I had only input and output. I have report and various files once the simulation is complete. Let me continue through my presentation. So this completely eliminates the human intervention. I cannot, I need not keep concentrating on the CFD part. I just have to produce one script and ensure that all the steps that are required for my analysis are included in the script so that it does all job for me. Yeah, so just like I mentioned, this is the automation ribbon where you can run the script. Let me open a new window and show what is actually happening. So there are two ways in which you can completely automate your process. One way is you can write Python script on your own and enter them here. That is one way. In another way is you are actually performing a operation on this modeling window, and software is writing that command in the background, and you're using that command for your next simulations. So let me show you what is actually happening. Let me import a CAD manifold input text. Yeah, this is the parasolid file. I'm importing it here. Yeah, I just imported the model. So what actually happened is software understood that user has imported a parasolid format. How we can see that? We can see it here in the automation, scripting, open session script. Here you will understand that, yeah, initially my unit system is set. It is in the MMKS, and in the next import parasolid. So this is the command which software understood that user has imported a parasolid. And all the operations, all the options that are related to the parasolid are enclosed within the table codes. So it is starting from here and it is ending it here. So all these options are related to the import options. And then finally in the last line, you can see there is a simlab.execute, which is import parasolid. So I have not written this command. This is automatically written in the background based on what user has done in the modeling window. So this is called process-based automation. Whatever you are doing in the modeling window, it is automatically written. Later on, what you can do is you can export this. You can say script, save session script, and you can save it in the .py format, and you can use this script for the various models that you have. So there are few things which you need to concentrate is while generating the script, you should generate a script in such a way that it is not specific to this model. It is specific, the script generated should be generic. I mean, next time if you import a different model with different dimensions, that script should work absolutely fine. It should not give you an error. So how to do that? There are few best practices to follow. So let me do one thing. Let me quickly do the surface mesh for this. So I'm going to the mesh, surface mesh, select this. I'm giving the average element size as some 10 just to save the time. Okay. It is generating the surface mesh. You can see the status here. Okay. So the surface mesh is complete. So just like I mentioned, whatever the activity that you are doing in this modeling window is automatically recorded in the Python language. So you can see that here, open session script. What we did, we imported a parasolid file. It is here. And then we did a surface mesh. This step is also recorded. So I have given 10 as the average element size. It is also recorded. So this way, whatever you are doing here is automatically recorded. So in the next stage, uh, let me quickly do the volume mesh also. So this is my, okay, before doing the volume mesh, I need to create few groups. So one best practice to follow while generating this script is you need to create groups. Now, this is my inlet and these are my outlets. So what actually happens is when I'm clicking on this face, so it is actually noting the ID here. So software understand that this surface has this face ID, face 267. But this is not common to all the models. Once you import this model back, this face ID changes actually. So the script, whatever that you have generated, is not applicable to that model. So your simulation terminates. So that is why it is important to create groups for generating the script. So how to create that? There are few ways. So one way is just look at my screen now. I'm clicking on this manifold fluid. The entire model is selected. Right clicking. I say select features. Then I say select planar faces. So this is the planar face, right? That is why I'm clicking on the planar face. So it is in the direction X. So what I do, filter features, define modifier direction, I say X. So whichever the planar face is in the X direction, please select that. That will be my inlet. That is what I am going to tell to the software. So I'm going to say OK. Here there is an option to create a group. Yes, I want the group to be created. I name it as inlet face. I say inlet face. So let me see what actually happens when I press on OK. Yes. So you see that it has automatically selected this face as the inlet. So what happens is next time, whatever the model, the identical model that you import it in the modeling browser, so it will not look for the face ID. It will look for this inlet face. So that is the best part of uh, generating a script using groups. So now I want these faces to be detected and these faces are going to be my outlet. So how to do that? Let me select manifold fluid, select features, planar faces. These are in the Z direction. So Z, say OK. These are going to be my outlet faces. Once I do this, I say OK. Yeah, you can see these four faces are selected. So these are going to be my outlet. So this is how groups are created in SimLab for scripting. So in the group section, you can see there is one inlet phase and there is one outlet phase. So these two phases are sufficient for this simulation. So I will go ahead with CFD mesh and generate it quickly. Ignore boundary layers on these groups. Yeah, you can see I want to ignore boundary layers on inlet and outlet. So I'm not going to click on these surfaces. Why? Because if I click here, it will record the ID. I don't want this ID to be recorded because it is not going to be the same for all the models. So that is why the best practice is to click on these groups. So it has selected, let me say 0.1 and let me say 15 mm and say OK. So it will generate a volume mesh. It takes few seconds to do that. Yeah, it is complete. You can see the volume mesh is successfully generated. Yeah, you can see volume mesh is successfully generated. So what actually happened? We did 3 to 4 operations in the modeling browser. Let us see what actually happened in this script. Script automatically updates after every operation that you do in the modeling browser. Yes, you can see it here. We did surface mesh. After that, we did select features. We selected a face and we created a group called inlet face. That should be written somewhere here. Yeah, it is there, inlet face. We created a group for inlet face. Then we created a group for outlet face. This is the outlet face. Then we created a CFD mesh. We gave value as 15 mm. It is recorded here. So this is how the software is automatically writing the code in the background for the whatever operations that you are doing here. So now I want the simulation to run. For that, I need to set up a flow simulation. Solutions, flow. I want to select these. Yes, this is sufficient. Let it be a turbulent flow. Say OK. So I created a solution. Even that will be recorded. So everything, whatever you are doing is recorded. This is the create solution, which is recorded here. So here I will assign a material. While assigning material, I'm clicking on this, say material. I want it to be water. Then I want inlet and outlet conditions. So select phase. Yeah, just like I mentioned, I don't want to select it directly. I don't want the ID to be recorded. I want to select by group. So this is my inlet phase. Yeah, you can also change the units here. I'm saying OK. Now if I go to outlet, I'm selecting outlet phase, say OK. My simulation setup is complete. I just need to run the simulation. So if I say update, it will quickly run the simulation for me. We can see the log file here. Yeah, time step 1, time step 2, the iterations time step has already started. I expect it to be converged at 15th or 20th iteration. Let's see. Yeah, the simulation is complete. Yeah, you can see the various counters here. Velocity, if I take a slice, it looks something like this. So my intention is to perform one simulation. I don't want to repeat these simulations again and again. That is why I am focusing more on the scripting part. So what I can do now is whatever the steps we have done here, all the commands are automatically recorded. You can see export and solve. What we did, we just submitted a job to the AccuSolve. It has completed the simulation. Then it is the post display mode. Then it has automatically directed us to the post processing. So once this is done, what I'm going to do is I'm going to save this file. Scripting, save session script. So I give some name. Let me say manifold flow. Yeah, so it is in the .py format. I save this file. So next time, uh, for other models, if you bring any different model, this script should automatically work for you. Yeah, this is the manifold.flow file. Edit with Notepad++. Yeah, you can see all these commands: import parasolid, export, transform, yeah, surface mesh. So in this way, you can completely automate your process. You just record the steps, then you copy all the Python codes that are written in the background and you organize it in the .py format. And in the next time, it is not necessary that this script works only for this model. You bring any identical model with different dimensions, this script should ideally this script should work. So that is the main intention of today's webinar. So let me go through my next demonstration. Yeah, here you can see I have a model. In the earlier case, we had direct fluid cavity. But in this case, we don't have a fluid cavity. We have a solid part. And what I need to do is, I want to perform a CFD simulation on this. So what are the different steps that are involved in doing the CFD simulation? Just like we discussed in the earlier slides, we have pre-processing, we need to do meshing, we need to do the physics setup, we need to do the solver run, we need to submit the job to the solver and then do the post-processing. In pre-processing, what you need to do is we need to import. If there are any unwanted features of geometry, we need to remove them. That is what is defeature geometry. So here what I'm going to do is I'm going to remove these holes. These are not required for my simulation. Then I will do the fluid cavity extraction, which is critical for my simulation. Then connect solids. In the meshing, I will be generating surface mesh, volume mesh. In the physics, I need to do all the steps: boundary conditions, material assignment, solution setup, run, and post-processing. Just imagine if there is no script, how much time it may consume. So for even for an expert, it will take anywhere between 40 to 45 minutes to do. Okay, even if we complete one simulation, what if we have similar kind of models? What if I have 10 to 15 models of similar size, similar dimensions, identical shape? I need to perform CFD simulation for each of the model. That I can completely eliminate by generating one script. So I will do this activity uh, with a script. I have it prepared for me in our demo. So manifold conjugate heat transfer. You can see again, I have a three folders. In the input, I have a model and I have a Python script. Let me open this script and show. Yeah, you can see it is importing a parasolid. It will export and it will save. It will transform. It will remove holes. It will extract the fluid domain. It will do the Boolean operation, surface mesh, unmerged bodies, select features for grouping. So it does all the steps automatically one by one without my uh, interaction, without the user interaction. So let's run this. Okay, before that, yeah, I forgot to copy them and paste it in the output. I will copy it and place it in the output folder. And let me copy this path and see what happens when I run this. Let me take a new automation, scripting, play, auto. This is how you run the Python script here. Okay. Yeah, I said it will take anywhere between 40 to 45 minutes for an expert. Let's see how much time the script takes. Yeah, you can see automatically the holes have been removed, fluid cavity is extracted, the solid is connected, and it is currently doing the meshing. You can see it in the status here. Mesh is complete. Unmerge is complete. We have two bodies, one is fluid body and one is solid part. Yeah, currently it is doing the volume mesh. Once it is complete, yeah, it is complete. You can see the icon is changed. It has automatically assigned the material. The material is water for the fluid body and steel for the outer body. And currently it is running the simulation. You can see the status in the left bottom here. So I'm doing nothing. I have all the steps recorded in the Python file and it is doing the job on its own. And in the end, when the simulation is complete, it will also generate the report automatically. So whatever the results that I have requested, whatever the results I have included in the Python file, that will be displayed. Yeah, you can see the simulation is complete and my model is here. The run result file is ready for me. Let me see what happened to the folder. Yeah, you can see this is my report, which is automatically generated. This is the temperature contour. This is the velocity contour, pressure contour, temperature slice plane, velocity, and pressure. Isn't it amazing? So all these steps, all the activities done in a single click. And even if you want any extra results, the result file is already loaded. You can do any post processing that you are interested in. Simulation is completed within hardly it took some 3-4 minutes. So that is the beauty of scripting. In the next slide, I have one more demonstration for you. I have prepared two demonstrations just to explain that this script doesn't work only for few problems. Whatever the problems that you are doing in the SimLab, whether this is a conjugate heat transfer or internal flow simulation or anything it can be. So you can plan to generate a script for your project so that you don't have to redo the simulation. You just run the script, you just prepare script once and rerun it again and again. So in the next demonstration, I have a flow wall. You can see in the image here in this slide. This is the wall. What happens is the flow enters from this section and it leaves the wall from this section. So in between, we have a plug. So in the wall designing, the profile of plug plays a very important role. So they need to optimize this for the best performance. So we need to redo the simulation again and again. So scripting actually helps us in this case. So it is not just about one simulation. We need to do the simulation for various plug travels. Currently, it is in the closed position. We need to see the wall, uh, the flow behavior inside the wall at various plug moments. So what if I have a script and run it again and again? I don't have to worry at all. So let me do that for you. Just like I mentioned in the pre-processing, these are the steps which need to be followed for this case. Then the meshing is common for all surface and volume mesh. Physics setup, we need to create a solution, material assignment and boundary conditions and the solution settings. Submit the job to the solver and then prepare a report. Even this process can be automated. So I have prepared a script. Let me run that also quickly. All simulations. So in the input, you can see I have a model and I have a Python file. I will copy them and paste them in the output folder. Yeah, let me run this. Let me take a new window, automation, scripting, play. Yeah, let's see what results I get after running the script. Yeah, import is complete. You can see various parts that are associated with the model. Okay. Yeah, actually it is running, but what just happened is it moved out of the window. Yeah, it takes some 2-3 minutes to complete. You can see the status in the left bottom here. You can see it has automatically captured the fluid body and then it has done the surface meshing. Currently, it is doing the volume mesh. Volume mesh is complete. It has assigned the material as water automatically. And this I am going to do for the plug travel of 10 mm from the close position. Yeah, I will show you afterwards. So all the steps are included in the script. Yeah, currently it is running the simulation. The job is directed to AccuSolve. The solver is running. And in few seconds, the simulation will be complete and we will be able to see the results. Few more seconds. Just for the demonstration purpose, I have generated a very coarse mesh. In order to get a accurate results, I need to modify the element size that I have used here. So I'm not concentrating on that. My aim is to show the automation capabilities in the SimLab, how you can generate the script and how you can reuse the script for various identical models. Yeah, we can see the simulation is complete. Yeah, I have my results ready. It took hardly 4 to 5 minutes to complete the simulation. So in the results folder, I have the presentation already prepared, automatically prepared. I have a velocity counter, pressure, and this is my velocity slice plane. This is my pressure slice plane. So if you want to do any further post processing, you can directly do it here. The result is complete. Let me open a cut section and see what actually happened. Let me take it to the Z. Let me keep it in the velocity. Yeah, you can see this is my flow distribution. Let me change the legend. It is currently 38. Just like I mentioned, I generated a coarse mesh. Yeah, at 5 meter per second. This is how the flow is. This is how the flow distribution inside the wall. It is entering from this section and leaving, passing through these gaps and leaving from this section. But if I change to pressure, the pressure counter looks something like this. So this is how you can completely automate your simulations in SimLab. Let me go through the further slides. Yeah, I have a case study to show. This is about CFD analysis of aneurysm with stent. Let me not take the name of the prospect here, but what they do is they are the leading solution providers in the healthcare industry. So what they do is they manufacture stent with different configurations. So this is actually inserted into this, and this bulge section is actually called aneurysm. So if I go to Google and type aneurysm and stent, you will have a good idea on this, what actually it is. Yeah, here you can see this is inserted into this and it is kept for the longer time, like 5, 6 months. And yeah, after keeping it for longer time, it actually, this size reduces. So what they do is they prepare different configurations of this tent and they want to do the CFD analysis on this. So can you imagine if they have 50, 60 number of configurations, different configurations? It is not ideal to do the simulations for each of the configuration. So they used this feature of SimLab, that is automation part of SimLab, and they were able to get the results in minutes for each of their configuration. So this is how it actually looks like. This is the configuration of stent. Yeah, these are some of the results to show this is the velocity at the inlet of aneurysm. This is how it is. These are the vectors. And you can see what actually is happening without stent and with stent. So these kind of CFD simulations, they were completely able to do with automation part of SimLab for their number of stent configurations. This is the pressure counter at mid aneurysm. You can see the pressure distribution, what is actually happening without stent and with stent.